Hello YouTube, today we are going to talk about transformers. And they deserve the name since they can be put alongside the great inventions that really transformed our lives forever. It made it possible to efficiently transmit electrical energy to long distances and convert power line voltages and currents to almost any value needed. Invented in the 19th century, today they are everywhere, conspicuously in power plants, electrical substations, and on utility poles, or hidden in your home electronics and AC adapters. The magic behind the transformer resides, as one would expect, in a convenient arrangement of materials, layout, and laws of physics. Any current will produce a magnetic field whose intensity is directly proportional to the current intensity. If the magnetic field changes with time, it will induce an electric field. Particularly if you consider a closed perimeter of a flat area A, with a perpendicular magnetic field B, this can be translated by a voltage V that is equal to -A times the rate of change of B with respect to time. The notation dB over dt is technically called the derivative of B with respect to t, the time. If you are not familiar with derivatives, please watch this previous video on the subject. If you wind two separate loops of wire around the perimeter of two flat, identical areas and make all the lines of magnetic field cross both, any change of the magnetic field with time will induce the same voltage on them. If you connect these loops in series, the resulting voltage will be double. It is easy to deduce that with n loops in series you will have n times the voltage of one loop. Now if you wind two coils with n1 turns and n2 turns respectively under the same magnetic field as before, you will have n1 times and n2 times the voltage of one turn. From this you get that the voltage ratio is proportional to the turn ratio. Suppose that we now connect an alternating voltage source to one of the coils, which we are henceforth going to call the primary. Since this is a voltage source, it will impose the voltage on the coil terminal and will try to supply whatever current this coil will demand to maintain this voltage. The coil will respond with a changing current that will produce a changing magnetic field that in its turn will generate a counter-electromotive force that will be exactly the voltage of the source. We make the changing magnetic field generated by the primary go through the other coil that we are going to call the secondary, and this will produce exactly the same voltage per turn, producing a total voltage that will be proportional to its number of turns. Up to now we have half of the magic. The other half happens when you connect a load to the secondary. This will make a current flow, which will generate another magnetic field. If this is to a changing magnetic field, it will tend to generate a counter-electromotive force on all the loops of both windings. But wait, we have a voltage source connected to the primary which will not tolerate any other voltage to be there except for the one it imposes. It will then supply a current that will generate another magnetic field with an opposite direction but equal intensity of that generated by the secondary current, so that they cancel each other. The net magnetic field in the core will be the initial magnetic field Bm only, no matter how much power is transferred from the primary to the secondary. Since the magnetic field produced by each turn is proportional to the current in them and each turn contributes equally to the total magnetic field produced by the coil, it's easy to deduce that the current will be inversely proportional to the turn ratio of the coils. Since all the power the secondary demands is provided by the primary, we conclude that, in this configuration, the transformer does not store energy, except for the energy of the excitation magnetic field Bm, which is necessary to maintain the voltage at the secondary. Using the two equations above, we can deduce that the impedance seen by the primary is equal to the impedance seen by the secondary multiplied by the square of the turn ratio. We can now draw this ideal transformer model, very useful in many cases for simplification and approximation purposes. Although in theory we could try to transfer whatever power to the secondary. We cannot, however, apply whatever voltage to a real transformer nor allow whatever current to flow. Transformer coils are frequently wound around some kind of ferromagnetic core. This is so because it offers high permeability and is cheap to produce. A high permeability means low magnetization current and high coupling, the guarantee that almost all lines of the magnetic field produced by the primary will cross the internal area of the secondary and vice versa. The failure of doing so would mean a leakage inductance in series with each winding. This would affect the ability of the transformer to maintain a good voltage regulation. All this benefit comes with a trade-off. Ferromagnetic cores can saturate, that is, the net magnetic field cannot be more than a certain value. Supposing you have a sinusoidal magnetic field. For a certain frequency and core area you will have a maximum voltage per turn that will be proportional to the frequency, the area of the core and the peak magnetic field. Leading a transformer into saturation will cause the magnetizing current to produce high peaks. The effect of the magnetizing current will be seen as an inductor in parallel with the primary. The friction of the core's internal dipoles when repetitively aligned with the magnetic field produces losses. This will be viewed as an equivalent resistor in parallel with the primary. Although nonlinear in character, this effect, called hysteresis, is modeled as a constant resistor for simplification purposes. If the core is conductive, the magnetic field inside will induce what is called eddy or Foucault currents, which will produce losses too. This is added to hysteresis loss to compose what are collectively known as core losses. They are proportional to the peak magnetic field, the frequency and the core mass, and are represented by a resistor in parallel with the primary. The wire is normally made of copper, sometimes aluminum, and will dissipate some of the power provided by the source. This will be seen as resistors in series with each winding and will affect regulation. And with this we can have the equivalent circuit for a transformer that is closer to reality. Of course there is a great deal of other effects we are not considering, like the capacitance between the windings, the skin effect, the rise of the wire resistance with temperature, etc. But for the purposes of our present discussion, they can be put aside. In practice, for many applications, the magnetization inductance is much greater than the leakage inductance of the secondary reflected to the primary plus the leakage inductance of the primary itself. And the core loss resistance is much greater than the wire resistance of the secondary reflected on the primary plus the wire resistance of the primary itself. This means that we can use an approximate equivalent model that is more suitable for analysis and testing. And with that in mind, we can now take practical aspects into consideration for designing transformers. Thanks for watching. Have a good night and stay beautiful.